Somewhere over the Atlantic, a tropical storm named Arthur just did something no computer model said it would. Billions of tons of water and wind are now moving along a path that every forecast called impossible, and the machinery that built this storm is still running. You may not have heard of Arthur yet. It formed quietly, in late May, in a stretch of ocean that usually swallows storms whole. But the quiet is over. What was supposed to fade into the open sea now points at something far more fragile, and the shift happened fast enough that forecasters are still catching up. The question is not where Arthur is, the question is what changed underneath it, and why that change kept multiplying. To understand what makes this storm different, we need to go back to where all storms are born. Where storms begin. Every tropical storm starts in the same patient way, over open ocean near the equator, where the surface water holds heat for months on end. Sunlight warms that water to 80 degrees and beyond, and each degree of warmth becomes fuel, stored in the sea, like a battery waiting for a spark. That spark arrives as a cluster of thunderstorms, drifting westward on the trade winds. Here the rotating earth does its quiet work, bending the rising air with the Coriolis effect, so that a loose pile of clouds slowly begins to turn. Warm air climbs, cools, condenses, and releases the heat back, which drives more air up. Pressure falls at the center, the spin tightens, and a disturbance becomes a depression, then a named storm, then something that can reshape coastlines. It is a slow, patient sequence, written into the physics of a spinning planet. Arthur followed that script perfectly, until it didn't. Arthur's birth. Arthur was born off the coast of West Africa late in May, drifting off the continent as a band of unsettled weather. Satellite images caught it early, a textbook low-pressure system with a round, well-organized center, and the National Hurricane Center gave it a name before the month was done. This was the routine version of a storm story, the kind forecasters have logged hundreds of times. The numbers were ordinary, the wind speeds unremarkable, and every model agreed on the same simple forecast: a westward crawl, a slow bend north, and a fading death over cooler water. There was something almost gentle about watching it take shape, a storm assembling itself exactly as the textbooks said it should, each swirl and band in its proper place. It looked like a storm with nothing on its mind but open ocean. For 3 days, Arthur moved exactly where the models said it would, and then the Atlantic had other plans. The first deviation. On the 4th day, something small appeared on the satellite loops, a half-degree wobble that the naked eye would never catch. Arthur nudged left of its predicted line, then settled back, as if correcting a course correction that was never made. The European model drew one path, the American model another, and for the first time, the two maps disagreed about where this storm meant to go. Models don't argue without a reason, and the reason was down there, deep below the surface, in water that was quietly, steadily doing something unusual. Meteorologists called it a minor fluctuation, but the ocean beneath Arthur was already whispering something else. The engine below. Tropical storms are not powered from above. They are fueled from below, by a layer of warm water thin enough to feel generous and deep enough to matter. Cross the 26.5 degrees Celsius line, and convection takes off, a storm's engine pulling heat from the sea and feeding it skyward, building cloud towers like a furnace drawing air. Each degree warmer means more energy available to the rising air, stronger updrafts, a taller eye wall, a storm that breathes harder and longer. The water is the gasoline, and the storm is the flame, and the relationship is relentlessly one-sided. A hurricane does not so much live in the ocean as drink from it, and the more it drinks, the more it grows. The water Arthur was crossing wasn't just warm, it was anomalously warm, and that changes everything. The heat anomaly. In 2024, a marine heatwave stretched across the North Atlantic, a vast pocket of ocean running 2 to 3 degrees hotter than the charts said it should. It was the largest sustained anomaly in the satellite record. one of those quiet superlatives that only scientists tend to mark down. Arthur was crossing the warmest water it would ever meet, a reservoir of heat that had been building for months, and the storm, still technically unremarkable, began to draw on that reserve. The engine below was running richer than any forecast had assumed. Subtle shifts began to show up in the models, intensification windows no one had predicted, a tightening core where the satellite had shown loose bands. Arthur was changing, though slowly, the way water changes before it boils. But heat alone doesn't explain where Arthur was headed next. Steering currents. Every tropical storm is carried, not driven. It wanders, but it cannot choose its road, because above the ocean, a network of winds and high-pressure systems decides where it may go and where it may never go. The Bermuda High is the gatekeeper, a giant dome of sinking air parked over the Atlantic. It acts like the rim of a bowl, steering storms that brush its southern edge along a corridor that runs straight toward the Caribbean, or curving the ones that ride its western flank north and out to sea. For 6 days, the models all said the same thing. Arthur would never reach land. It would ride that western flank, curve northeast like 100 storms before it, and wander into water cold enough to kill it, far from any shore. Arthur was supposed to curve northeast and dissipate over cold water, except the Bermuda High collapsed. The collapse. On day 6, the pressure maps began to change. The high that had stood like a wall for a week thinned, then broke, and weather stations watching their barometers saw readings fall where they should have held. Where a wall of sinking air had been, the maps now showed an open corridor, a gap wide enough to swallow a storm. The rim of the bowl was simply gone, and nothing stood between Arthur and the deep tropics. That vacuum turned the steering upside down in hours. The winds that had promised to push Arthur north now had nowhere to push against, and the storm, no longer held, began to answer to the only force left in charge. With nothing to push it north, Arthur did what storms do when left alone, and it followed the heat. The new track. By the next morning, the official track had been redrawn. The arrow that had pointed out to sea now bent west, and the cone of uncertainty stretched across the Lesser Antilles like a shadow moving over a map. Islands that had spent the week expecting a quiet season sat inside that cone. Emergency advisories went out to governments that had not prepared for this. Shelters opened on beaches that had been full of swimmers the day before. Barbados, St. Lucia, Dominica, the arc of small nations strung across the eastern Caribbean, each one now watching a storm the models had sworn would never come near them. But the storm wasn't just moving west, it was feeding on something the models hadn't accounted for. Loop currents. Beneath the surface of the sea runs something a storm learns to read. The Gulf Stream and its branch, the Caribbean Loop Current, are rivers of warm water moving at their own pace, some of them older than the storms that cross them. These currents do not just heat the surface, they carry pockets of deep heat far below, reservoirs 100 meters down, where the water holds its temperature through the night, and the next day, and the next. Ships and buoys measure their edges, but satellites see only the top few centimeters, and so a warm pool can sit there, vast and dark, unseen from above. A hurricane crossing one of these pockets finds fuel no forecast fully priced in. The heat below feeds the engine that drives the whole storm, and the storm drinks until it changes. Arthur crossed one of those pockets on day 8, and within 12 hours it became a different storm entirely. Rapid intensification. The numbers tell the speed of it. 65-mile-an-hour winds, then 90, then 110, all inside a single day. The pressure at the center fell 35 millibars, and storms do not do that gently. On the infrared satellite, where a swirl of cloud had sat for a week, there suddenly appeared an eye. A clean circle staring back at the cameras, the signature of a storm reorganizing itself from the inside out, pulling air and moisture into a tighter, faster spin. This is rapid intensification, and it is the most violent hour of any storm's life. The ocean vents heat upward in a rush, the cloud tops crackle with lightning, and for a while, the storm is simply growing faster than anyone can track it. The question meteorologists were now asking wasn't where Arthur was going, it was whether anything could stop it. Wind shear. There is one natural break that kills hurricanes all the time, and its name is wind shear. Not the wind at one altitude, but the difference between winds above and below, a change in speed or direction as you climb. A hurricane is a tower, and it needs its cloud tops to stand nearly straight above its center. When winds push the top of that tower sideways while the bottom stays put, the storm tilts. Its heart and its reign separate, the structure slumps, and a Category 3 can unravel into a wandering squall before it ever reaches a coastline. Forecasters scanned the atmosphere ahead of Arthur, looking for shear that could save the islands, and found almost none. The atmospheric window. Low wind shear, then, is the exception Arthur burned through. What mattered was what occupied that space instead, a column of warm, moisture-heavy air that reached several miles up, sopping enough that rain clouds could build without drying out, plus a sea surface running nearly 2 degrees above the long-term average. Historians of the Atlantic point to a few storms that moved through the same rare alignment, the same open door. Each one kept its strength across open water where others would have withered, and each one is still cited in training manuals as the case you don't forget. Every ingredient tilted Arthur's way at once. Low shear, warm water, moist air stacked like a lock with all the gates open. A corridor, effectively, with no reason for the storm to spend its fuel. What comes next is the part that still doesn't make sense to anyone who's studied Atlantic storms for decades. The stall. On day 10, Arthur stopped cooperating with its own forecast. The forward motion that had carried it west at 15 miles an hour bled away to a stuttering 3, then to nothing at all, and the storm simply sat. 18 hours it hovered over one patch of ocean, east of the Windward Islands, churning the same water. A stalled storm is a flooding machine. The rainfall that would normally sweep across a coastline in hours instead lands in a single place, and the ocean beneath keeps feeding the updraft. Forecasters warned of totals that would sound exaggerated a week earlier. Yet the satellite images told a stranger story, because the cloud field stayed tight and tall. A storm that is dying drifts apart and loses its shape. Arthur kept its structure and refused to move. A stalled hurricane is dangerous enough, but Arthur wasn't stalling because it weakened. The wobble. Then the tracking loops began to show something off. The storm's center, instead of holding its position or resuming its path, started tracing a slow figure 8, drifting back over the water it had already moved through, hesitating, pulling east again in a way no forecast had predicted. Meteorologists stared at the animation frame by frame. Between stall and steady motion there is supposed to be a clean answer, and Arthur was giving neither, its core oscillating like a pendulum waiting for a push. A single storm does not move like that on its own. Something outside, unseen on the conventional maps, had to be reaching across that stretch of ocean and tugging at the storm's edges, though the name for it would not come until later. The real question is, what was pulling Arthur off course, and the answer appeared on satellite 3 hours later. The twin. 3 hours later, the satellite found something the models had missed. A second low-pressure system sat 400 miles southwest of Arthur, spinning quietly beneath a convective burst, and it already had a name, Bertha. It had been nursed into being by the same unstable air that fed Arthur, a stray eddy of thunderstorm energy nobody thought to watch. For 2 days it stayed small, unremarkable, the kind of system that usually dies by morning. But Bertha did not die. It deepened. And as the 2 low-pressure centers settled into the same patch of ocean, a strange effect began to show in the tracking data. Arthur's path curved. Even as every steering current said it should hold course, it curved toward the other storm. It was being drawn. Storms dislike a vacuum, but this was more than barometric arithmetic. When 2 storms get close enough, they stop behaving like weather, they start behaving like celestial bodies. The Fujiwara effect. There is a physics to two storms sharing an ocean, and it was first described in 1921 by the Japanese meteorologist Sakuhei Fujiwara. Watching typhoons in the Pacific, he noticed that two cyclones within about 900 miles of each other do not push past one another. Instead, they begin to orbit, pivoting slowly around a point between them, like two dancers circling a shared center of gravity. Each storm wraps its circulation partway around the other, and the whole system rotates as a single pair. It is the same math that keeps binary stars locked in their mutual embrace, the same gravitational choreography that governs planets. Weather, it turns out, can obey orbital mechanics. Arthur and Bertha were now locked in a slow dance, and no model could predict where that dance would end. The dance. For 12 hours, the two storms rotated around a point that belonged to neither of them. On satellite, the imagery turned hypnotic. Two great spiral arms reaching across the water toward each other, like fingers stretching through a dark room. Where they nearly touched, the pressure gradient grew brutal. Air rushed down that narrow corridor at speeds no single storm could have produced, a wind field that defied every rule forecasters read from a single center of circulation. The models thrashed. Each run offered a different outcome, then a different one, then a different one still. Some solved the pair by absorption, some by separation. None of them agreed. Forecasters watching this unfold knew one of two things would happen, and both were dangerous. Merger or separation. In theory, the mathematics offered two exits from the dance. In the first, the two circulations locked together and swallowed each other whole, one system devouring the other until a single, larger storm remained. In the second, they passed close enough to wrench each other's tracks sideways, slinging apart into two altered paths that led somewhere no forecast had drawn. Which one would play out depended on distances measured in miles and timings measured in hours, a braid of variables no model could hold steady. Some runs ended in absorption, others in separation, and the spread between them widened with every 6-hour cycle. The Atlantic sat with its arms crossed while the computers argued. Meteorologists on their midnight shifts kept refreshing the same frames, watching the gap between the two storms shrink by a mile here, a mile there. Each shift brought the moment closer, and each model disagreed about what that moment would deliver. By dawn on day 12, the answer became clear, and it was the worse of the two. The merger. Bertha's circulation began to unravel around its edges first. Its outer rain bands, instead of holding their line, curved inward and wrapped themselves around Arthur's core like thread finding a spool. The smaller storm stopped being a storm and started being a meal. The central pressure started to fall, and it fell fast. As the two engines fed into a single heart, the walls of the eye contracted, tightened, and reformed into something rounder and far more organized than either system had been alone. The combined vortex drew in warm ocean air from every side and turned it into wind. What emerged wasn't just a bigger storm. It was a storm with a memory of two separate heat sources, two histories of absorbed energy still churning inside a single eye. The hybrid core. Up close, the hybrid was stranger than a simple sum of its parts. Radar showed not one ring of maximum winds but two, a double eye wall that pulsed like a heartbeat under the cloud tops. Convection fired off in lopsided bursts, the storm behaving less like a single machine and more like two engines running on a shared chassis. History offered a grim precedent. Hybrid systems like this one have a habit of ignoring intensity forecasts entirely, strengthening at rates the models refuse to believe until the satellites catch up. The mechanisms are still debated, but the outcome has been the same each time, a storm that outruns every prediction made about it. And now, with nothing left to disrupt it, Arthur resumed its march west, directly toward the Caribbean's most vulnerable coastlines. The islands. The Lesser Antilles are a string of green beads flung across the ocean, hundreds of miles from anywhere. Each one a small nation with a single main road ringing the volcano at its center. Hospitals built low on the shore because that is where the flat land is. These islands have weathered storms for as long as anyone can remember. Generations of islanders know the rhythm of hurricane season, the way they know the tide. But they had never faced a system like this, one that had stalled, reorganized, and gathered strength over water that had never been this warm, on a path the old storms never took. Forecasters watched the projected track and measured the preparation time in hours, not days. Evacuation on an island means moving everyone to a single concrete school hall on the highest ground and hoping the roof holds. On day 13, Arthur's outer bands made landfall on Dominica, and within an hour, the reports started coming in. First landfall. The anemometer at Dominica's airport recorded sustained winds near 140 miles per hour before the instrument reached its rated limit and broke. Whatever came after, no one will ever have a precise number for. Storm surge pushed into the coastal villages first, then the river valleys funneled the rain inland faster than the roads could drain. The houses along the waterfront were small, timber and corrugated iron, built close together the way villages have always been built here. Some of them simply folded, others held, and their families huddled in the dark while the wind pulled at the roof, listening to the shriek of it for hours, with no way to know if morning would change anything. What the first daylight revealed was not destruction in the dramatic sense, but absence. The familiar shapes of the town were no longer there in the places they had always stood. But Dominica was only the beginning. The storm's true path was now becoming clear. The Caribbean corridor. Arthur's center bent northwest, and the projected cone now ran like a thread through the islands one after another. Martinique, then St. Lucia, then St. Vincent, with Grenada sitting uneasy at the edge of the uncertainty. Each island had hours of warning as its neighbor went dark, and no one needed to say what that looked like on the radar. The evacuation orders cascaded down the chain, each one arriving with less time than the last. On an island of 100,000 people, with one ferry dock and one small airstrip, moving a population in the window available is not a plan, it is a hope. Every road leads to the same high ground, and the high ground is small. What forecasters were watching for now wasn't just wind speed, it was whether Arthur would weaken over land or somehow maintain intensity. The terrain question. Mountain terrain is not a wall, and yet it behaves like one. When a hurricane's lowest winds slam into ridges and peaks, the friction of the land shreds the fine, ordered circulation near the surface. The storm loses its grip on the ocean at its base. And that base matters more than the winds aloft, because a hurricane is fed from below. Ridges tear at the inflow, break the smooth turning of the eye wall, and choke the engine that draws warmth up from the sea. Most storms that cross high islands pay for it quickly, shedding measurable strength in hours. So the arithmetic of the forecast was simple on paper. Arthur was about to climb straight over islands with peaks reaching high into its lower cloud decks, and storms that do that are supposed to weaken. The models showed it. The pattern said it. Every rule of the tropics wrote the same ending. Arthur crossed Martinique's peaks on day 14, and on the other side, it was just as strong. The resilience. And here is where the arithmetic stopped adding up, and the storm stopped caring. Arthur was not a small, neat thing that a mountaintop could tear apart. It was a system so wide that part of it never left the water. For every hour, its western flank clawed at the land, its eastern flank drank the open sea. The engine never died, because the engine was never fully ashore. It stumbled, and the stumble lasted a few hours, not a few days. Then the eye cleared the far coast, and the warm salt air poured back in, and the structure that had just been battered simply reformed. Witnesses described the same sky returning, almost on a schedule, as if the island had been a stone in a river rather than a wall. Meteorologists have a name for this, quietly, a storm too large to disrupt. There is no single mountain, no one ridge that can reach across a system 300 kilometers wide and shut it down. The islands became speed bumps, and Arthur rolled over them. By the time Arthur reached the open water south of Puerto Rico, it had done something only 3 storms in satellite history had managed. The Category 5. The storm's engine had finally reached full throttle, and the readings that came back were the kind meteorologists would spend years trying to forget. Winds held steady at 160 miles an hour. The central pressure, the measure of a storm's hunger for air, plunged to 920 millibars. The eye, that calm cathedral at the center of the noise, had contracted to a tight 12-mile ring. On the Saffir-Simpson scale, this earns the top tier, Category 5, the classification reserved for storms that have exhausted what most ocean temperatures can ever give them. Only a handful of hurricanes in recorded history have ever stood this tall. At this strength, the physics stop being academic. A Category 5 does not push against a coastline so much as erase it, stripping roofs, snapping steel, turning debris into a second storm of its own. The category is not a description of the wind alone, but of what that wind is capable of doing to anything built by human hands. Yet for all the awe that number carries, the rating itself wasn't what alarmed the National Hurricane Center. It was where Arthur was headed next. The Puerto Rico scenario. Puerto Rico had met a wall of wind like this before, and it still carried the scars. In 2017, Maria came ashore as a Category 4, reached an estimated toll near 3,000, took down the island's entire power grid, and left tens of thousands of blue tarp roofs showing from the sky years later. It was the strongest storm to hit the island in 85 years, and it left the largest blackout in American history. The island holds 3.2 million people, most of them pressed along a coastline that wraps itself around peaks rising to 4,000 feet. Evacuation here meant moving inland into the mountains, which was also exactly where the most water would come down. There was no long highway to the mainland, no wide escape route, just an island and the sea closing around it on every side. Every shelter, every road, every rooftop Maria bent, Arthur could bend again, and a population that had barely rebuilt had nowhere further to fall. For 36 hours, the forecast cone wobbled between a direct hit and a near miss, and then Arthur made a choice. The graze, the wobble resolved in the worst possible way, or else the best. Arthur's eye passed 10 miles south of the island's southern coast, close enough that the eye wall raked the shoreline, close enough that the sea rose hard against Ponce and Guayama. But the center never crossed land, and in a storm that single fact outweighs almost every other. Staying over water meant the circulation never dragged across the island's mountains, never had its heart torn open by their peaks. San Juan, sheltered on the north coast behind the Cordillera, watched the barometer fall and the sky turn strange, and then, slowly, the pressure began to climb again. The southern towns counted their roofs gone and their streets running, and the full scale of the damage would only surface in the days to follow. What nobody said out loud was how thin the margin had been. A shift of a few miles and the eye would have come ashore, and everything about the island's story would have read differently. The island was spared the worst, but the storm wasn't done, and its next target had no margin for error. Hispaniola. Beyond the Mona Passage lay an island where storms have always found their darkest errands. Hispaniola is shared between 2 nations, Haiti and the Dominican Republic, a land of deep valleys and peaks tall enough to tear the tops off hurricanes, and that is not a mercy. The mountains that break a storm's winds become the walls that funnel its rain, and rain in Haiti has a long memory. In 2004, Jean's floods killed an estimated 3,000 people there. Matthew in 2016, then George before either. The slopes are steep, and the tree cover is mostly gone, less than 15% of Haiti's land still wooded, so the water runs off bare earth and gathers into mud that slides. Roughly 20 million people live on this one island, many of them in homes of tin and timber that offer little against a storm of Arthur's class. There are few shelters that would hold, and fewer roads that would carry anyone to them. A cyclone does not need its full fury to do its worst here. It only needs to be strong enough for the mountains to finish the work. Arthur was now less than 200 miles away, and the models showed a direct strike on the southern coast. The weakening. Then the wind began to die. 8 hours. That's all it took. A Category 5, a storm that had earned every measure of dread, dropped to a Category 3 as it came against the wall of Hispaniola's mountains. The spine of the island reached up and tore the storm apart from within. Cooler water, drawn up from the deep along the coast, robbed it of its engine, and far away, a trough sent sheer snapping through the upper sky like a blade. The models had been right and wrong in the same breath. The fury was gone, but the weight was never about the wind. Even diminished, Arthur carried enough water to bury entire valleys, and that's exactly what it did. The deluge. The wind fails first, always, but the rain asks nothing of the storm's strength. Arthur had slowed to a crawl over the mountains, and in that stillness it emptied itself. 30, then 40 inches of water across southern Haiti and the Dominican Republic. Rivers that remembered their banks for a century forgot them in a night. Landslides erased roads as if they had never been drawn. This is the quiet arithmetic of disaster. Wind breaks a building in seconds, water takes a village and all the time it needs. More people die from what falls from the sky than from what the sky hurls. By the time Arthur limped away from Hispaniola, it was barely a hurricane, but the Caribbean wasn't finished with it yet. The resurrection. The Bahamas are warm, warmer than the sea it had just left, warmer than any water had a right to be, and a barely hurricane, ragged and spent, does what a storm always does when the fuel is rich and the wind is quiet. It fed, slowly at first, then greedily. The eye reformed where there had been only wreckage. Forecasters watched their screens and redrew the warnings for islands that had already counted themselves safe. Within a day, Arthur was a Category 2 again, and the dread crept back into every voice that tracked it. What was left of Arthur now faced a choice: turn north toward the Atlantic, or continue west into the most dangerous water in the hemisphere. The Gulf question. So which was it? A hard right turn into the open Atlantic, or a straight line into the Gulf? The computer models split into two camps, and the divide between them was the difference between a scare in the ocean and a disaster on land. At stake was a single feature, a trough of low pressure dipping down out of the north. If it swept far enough south, it would catch Arthur and drag it away from shore. If it stalled, if it failed to reach down and grab the storm, then nothing sat between Arthur and the warmest body of water on Earth. Forecasters watched that trough for days, and the models shifted with it, one run curling the storm east, the next driving it west. The trough that forecasters hoped would pull Arthur north stalled over the Carolinas, and the door to the Gulf swung open. Gulf waters. The Gulf of Mexico is a trap with no exit latch. It is a nearly closed basin, ringed by land, and the sun beats down on its shallow water all summer long, so the heat has nowhere to drain away. A storm that enters the Gulf does not enter a battlefield, it enters a reservoir that has been filling since spring. The water near the surface runs 30 degrees Celsius or hotter, and beneath that, currents like the Loop bring up warm water from 1,000 miles away. And there is the shelf, the seafloor that shelves off gently along the coast for miles and miles. A storm over deep water shoves surge that gets absorbed. A storm over that shallow shelf has nowhere to put its energy, so the water has to go up instead. Every hurricane that has ever terrified the northern Gulf came through this same doorway. Arthur entered the Gulf on day 19, and the water it found there was the warmest on satellite record. The Loop Current. Somewhere in the central Gulf, Arthur crossed the Loop Current. It is not a current you can see from the surface, just a slow river of deep blue Caribbean water that pushes its way in through the Yucatan Channel and coils down toward Florida. But its warmth goes deep. At 150 meters down, the water still holds 30 degrees Celsius, and that is the key difference. Most storms feed on a thin, warm skin, a few dozen meters of it. A storm over the Loop pulls from a well with no bottom. The pressure inside Arthur began to fall. fast, the way it does when a storm finds fuel it has never known. By nightfall, the eye had tightened, the winds had climbed, and the satellite images showed the classic ring of a major hurricane organizing itself overhead. The intensification was not gradual, it was explosive. Within 24 hours, Arthur had regained Category 4 strength, and now the entire Gulf Coast was in the cone. The cone widens. The cone on the forecast map stretched like a weather vane, pointing at 1,000 miles of coastline. From Brownsville, Texas, all the way to the Florida Panhandle, every beach, every bayou, every bridge sat inside the range of possible landfall. 5 states declared emergencies on the same afternoon. For officials, the math was brutal. An evacuation zone that wide is a logistics problem with no good answer. More than 100,000 people on the road at once, highways that were never built for that kind of traffic, shelters that can only hold a fraction of the crowd. Forecasters drew the cone wider with every run of the model, honest about what they could not know. The storm would come ashore somewhere along that enormous line, but exactly where was still an open question. But the storm's size was now the real problem. Arthur's wind field stretched 400 miles across, too large for any coastline to escape. The Louisiana memory. For Louisiana, this was not a new fear. It was an old one wearing a familiar face. Katrina in 2005, Rita the same year, Ida in 2021. Each storm carving a little more out of the coast. Each one leaving behind a scar the next one would reopen. The people who watched the cone knew this script by heart. The land itself has been sinking for decades, subsiding an inch or two every decade as the delta settles and the sediment stops arriving. Coastal erosion has pulled the marsh back mile after mile, so the surge now pushes farther inland than it ever could before. The levees surrounding New Orleans were engineered to hold back a Category 3 storm, with margins that assumed the ground underneath would stay put. Arthur was now aimed directly at the Mississippi Delta, and the levees designed for a Category 3 were about to face a Category 4. The wobble returns. Then came the wobble. For 2 full days, Arthur's center wandered, tracking toward New Orleans, stalling, then shifting 50 miles to the west, then sliding back. 50 miles. That was the difference between a city flooded and a city spared, between billions in damage and a narrow miss. The computer models split their answers, some calling for landfall at the delta, others pointing at the bayou to the west. Meteorologists do not get to promise certainty when the atmosphere refuses to cooperate, so they talked in probabilities, in percentages, in the honest language of a range of outcomes, each scenario weighted by the evidence, none of them certain. The message to the coast was simple: assume the worst, plan for every possibility, because precision is not something the sky owes us. On the morning of day 22, Arthur's eye finally stabilized, and the target became clear. Landfall. At dawn on day 22, the eye wall reached the coast. The wind that morning was measured at 145 miles per hour, and under that wind, the ocean did something almost mechanical. It stopped behaving like waves and started behaving like a wall. A 15-foot surge poured over the barrier islands, not as a crash but as a steady, patient rise. It did not need to break anything. It only needed to keep coming, and it did, hour after hour. West of New Orleans, the low ground drank the water the way it always has, only this time there was no room left to drink. The physics were unremarkable in the strictest sense. Wind pushes water, water climbs, land gives way. That is all a surge is, and that is all it needed to be. For 6 hours, Arthur ground across the coast, and when it finally moved inland, the ocean didn't follow the storm, it stayed. The surge. Here is the part that is easy to misread. When the wind and eye pass, people assume the danger leaves with them. But the water that was pushed in does not have instructions to reverse. Wind stops blowing and the sea stays high, trapped in the bays and estuaries it flooded on the way in. So the flooding kept climbing for hours after the sky cleared. What looked like the storm's end was actually its slowest, most patient act. a rise measured in inches per minute, not feet per second. This is called the delayed danger, and it carries no warning siren with it, no rolling wall of white water, just the soft sound of water finding its own level across streets and doorways and the things people keep on the ground floor. But the wind and water were only half of what Arthur brought ashore. The inland flood. The other half fell from the sky. Once over land, Arthur slowed to a crawl, 5 miles per hour at times, and a storm moving at 5 miles per hour is not moving away from anything. It is standing still, emptying an ocean of moisture onto ground that had been saturated for weeks. 20 to 30 inches of rain came down across Louisiana and Mississippi. Rivers that had already accepted their flood stage swelled again, and some would not crest for days. The water kept arriving after the storm's name had faded from the alerts. Coastal damage is violent and loud, so it gets the cameras, but the inland flood is bigger, slower, and harder to repair because it settles in and refuses to leave, soaking through the entire region long after the wind is a memory. By the time Arthur weakened to a tropical depression over Tennessee, it had traveled 3,000 miles and crossed 11 countries. The remnant. What remained of Arthur was no longer a storm. The circulation had unraveled, the warm core gone, and what was left was a broad, shapeless smear of moisture, dragging itself across the Appalachians and emptying out over valleys that had already been drinking for days. It merged with a frontal boundary, and the rain folded into something almost ordinary, a grey week of drizzle that locals would later call a bad stretch of weather. Only the damage told another story. The storm had already written its ending back where it began, in the open Atlantic, and the system quietly dissolved over water it had crossed 3 weeks earlier. Every hurricane is a life cycle, and Arthur's ran the whole arc, born from a wave off Africa, growing, weakening, resurrecting, then fading back into the sea that made it. The question everyone was asking now wasn't what Arthur did, it was what Arthur means. The pattern. Look at the last 2 decades of Atlantic hurricane seasons and a shape begins to emerge. A pattern too consistent to call coincidence. Storms are exploding from tropical depression to major hurricane in under a day now, a feat that was rare 20 years ago and is becoming routine. They are also moving more slowly, lingering over a coastline longer, wringing out more rain while they do. Arthur doubled down in the Gulf, sat nearly motionless over warm water, then dumped record totals across the Carolinas. Same ocean, same latitudes, but the arithmetic has changed. Warm air holds more moisture, about 7% more for every degree, and that extra water has to fall somewhere. The data shows something undeniable. Storms like Arthur are becoming more common, not less. Ocean heat content. But the surface reading only tells half the story. What matters more is ocean heat content, the depth and volume of warm water stacked beneath the surface, water that a storm can draw on for days. A warm top layer is a thin fuel tank. A warm layer 100 meters deep is a reservoir, and it doesn't drain when a storm passes over, it feeds the next one and the one after that. The measurements have been running since the mid-1980s, and they show a steady, unbroken climb in Atlantic heat accumulation, the ocean storing more energy each decade than the last. That's not a wobble in the data or a warm patch that will cool off. The ocean Arthur crossed wasn't just warmer than average, it contained heat that wouldn't have existed 30 years ago. The attribution question. Researchers who study storms draw a careful line between 2 very different questions. One asks whether climate change makes hurricanes more frequent. The other asks how much damage they do when they arrive. And the answer to that second question has become easier to give with each passing season. To test it, they build 2 versions of the same storm in the same computer model. One runs in the world as it is, with the stored heat. The other runs in a counterfactual world, the ocean Arthur would have crossed if the last 3 decades of warming had never happened. What emerges is a study in subtraction. The storm's path barely changes, its wind speed stays nearly the same, and rainfall, in the control run, comes down measurably lighter. That gap between the two sets of numbers is the shape of what our emissions have already done. Frequency is a weather question. Rainfall and storm surge are a climate question, and the models have grown confident enough to attach percentages to them. No single storm is caused by climate change, but the environment Arthur moved through was shaped by it. The rainfall signal. Arthur's strongest signal was not in the wind at all. It was in the water falling from the sky, and the reason traces to a piece of physics over a century old, called the Clausius-Clapeyron relation. For every extra degree of warmth, the atmosphere can hold about 7% more moisture, and that moisture must go somewhere. Satellite records show the air over the Atlantic now carries several percent more water than it did before the industrial era. Every drop of that is fuel, waiting to be condensed into rain. The warmer the air, the heavier the fall. There is a second, quieter shift working in the same direction, not just how much water a storm can hold, but how long it lingers over one place. Weakening steering currents, tied to a warming Arctic, have slowed the westward drift that once hurried storms past. Stalled over open water, a storm keeps its moisture high instead of exporting it. Slowing by just 10% can add a fifth to the rainfall that comes down. The wind speed might have been possible in any decade, but the water Arthur carried was not. Future storms. Run the models forward 3 decades, to the year 2050, and the picture sharpens. Climate simulations agree broadly on the arithmetic. Peak wind speeds a shade higher, and rainfall totals that keep climbing, in some projections by more than 20% before the century is half over. More telling is what happens to the geography of danger. Rapid intensification, the overnight leap that turned a modest storm into what Arthur briefly became, is projected to reach waters further north and further out of season. The places where a storm can suddenly swell will no longer be the ones we've learned to watch. None of this reads as prophecy exactly, and the models could miss in either direction. But every line of evidence points one way, and the direction is up. Storms in 2050 will not need to be stronger to feel different. They will carry more, stall more, flood more. The dangerous turn Arthur took wasn't random. It was a glimpse of the baseline we're building. The forecast challenge. Track forecasting has come a long way. A storm's path 48 hours out is now predicted with an accuracy that would have seemed impossible a generation ago. But where a storm will land is only half the question. The other half is how violent it will be when it gets there, and that is where the models still stumble. Arthur's core pressure dropped more than 70 millibars in under a day. That is rapid intensification, the forecast that bends toward chaos, because a storm that grows that fast is feeding on conditions too small and too fast-moving for the grid to capture. Some of that uncertainty is irreducible. Weather is a chain of tiny decisions, each one amplifying the last, and beyond a few days, no machine can hold the whole thread. Every storm teaches meteorologists something. Arthur taught them that the old rules are changing faster than the models can adapt. The infrastructure gap. The gap is not only in the forecast, it is in what the forecast is meant to protect. Stand at the shore and look inland. The houses, the seawalls, the drainage channels, the evacuation routes. Most of them were designed for the storms of the last century, drawn on paper when a Category 4 was the worst anyone could imagine. That was before the ocean warmed, before storms began to stall and swell in place. A levee built for a 5-meter surge, a roof rated for 50,000 newtons, a highway that becomes the only way out. Each one assumes yesterday's ocean. Adaptation moves in decades. The ocean moves faster, so the infrastructure waits for the storm to prove it wrong, then gets rebuilt 1 meter higher, one code revision late. Arthur exposed that gap in every place it touched, and the cost of ignoring it grows with every season. The human cost. In the end, the ledger is not measured in millibars or meters. It is counted in people. 12 nations, thousands of homes gone. Towns that will never be rebuilt the same way again. And who bears the weight is never even. The storm does not choose, but it does not need to. The lowest ground, the oldest buildings, the families with no car for the highway and no savings for the flight, they were always standing closest. The beaches where the rich rebuild get their walls raised. The low ground where the rest live waits for the next surge, because resilience is a luxury that arrives only after the destruction proves it necessary. But beyond the immediate destruction, Arthur changed something less visible and more lasting. The psychological scar. What the forecast maps never plotted was the cost carried inside a person. Months later, the drum of rain on a roof, the first wobble in an advisory chart, the air leaving a room before a summer storm could drop a family straight back into the worst hours of that season. The hurt does not fade the way we like to believe. Long after Katrina, researchers found 1 in 6 low-income mothers still carrying symptoms of post-traumatic stress 12 years later. The body keeps a ledger, the headlines rarely open. And there is the harder mathematics. Every new season asks them to rebuild while the old wound is still fresh, so the fear does not subtract from one storm to the next, it compounds. Someone who survived one season and then another carries both inside the same body, and the weight of two is more than either alone. There's a reason this storm is still talked about months later. It forced a reckoning. The reckoning. What made Arthur alarming was never a single record. The alarm lived in how many extremes lined up in sequence, each one feeding the next. A marine heatwave had loaded the water with stored warmth. A Fujiwara interaction, 2 storms turning around a shared center, nudged its path along. Then it crossed the loop current, that deep tongue of warm water that has fueled our most dangerous hurricanes for as long as we have watched them. Add a slow drift over land and an intensity that refused to die, and the old rulebook stopped applying. Models built on the statistical memory of the Atlantic found no line for that combination. So Arthur did not break one rule, it broke them in order, each failure revealing that the past no longer describes what the present can do. Arthur's dangerous turn was not a single moment. It was a cascading revelation that the atmosphere and ocean are now capable of producing storms we did not design our world to withstand. The lessons. Out of the wreckage came plain work. Forecasters are learning to hear the ocean's depths, sending Argo floats and underwater gliders ahead of a storm to measure heat where it hides below the surface, not just in the bright skin of the sea. Every reading is a small map of what a storm might drink. The models sharpened. The next generation of forecast systems caught the sudden rapid jumps of recent storms days in advance, and a few extra days can be the difference between a full evacuation and a last-minute scramble. Warning, in the end, is measured in lives. Builders measure to the new waterline, and coastal towns stagger their defenses so a single breach no longer floods everything. Officials came away with the hardest lesson of all, that some portion of risk cannot be engineered away, and people deserve to hear that plainly, without false comfort. Some of those lessons are being applied now. Others are still waiting for the next storm to force the issue. The next season. The ocean keeps its heat through the quiet months, and the forecasts for the coming season already call for above-normal storms. Nobody has to say the word aloud for everyone to feel it in the room. What's different is not the water and not the wind, but the remembering. Agencies run the drills now. Shelters are mapped before the first watch is issued, and a warning goes out in a voice that tells people the truth, even when the truth is uncomfortable. That is the incremental progress, slow and unglamorous, built in the years between disasters. It will not stop every storm, and it will not save everyone. It narrows the margin, and sometimes a narrow margin is the whole difference. So the next season comes the way all seasons come, measured and inevitable, carrying its quota of heat and uncertainty. We watch for it now the way we watched for Arthur, knowing the pattern and still unable to name the ending. Every morning that the horizon stays clear is a small mercy, and every warm patch of ocean is a question we cannot answer in advance. we face it the same way, alert, humbled, and hoping that this time the remembering does the work. The hurricane we followed was one name among thousands, one turn in a pattern older than any coastline. It changed the people who lived through it, and it left the view of the water slightly different for everyone watching. That difference is what we carry into the next storm, and the next, and the one after that. Thank you for staying with the story. If this is the kind of calm, patient telling you like, subscribe so we can weather the next one together.